MVPbev is a novel two-stage method for multi-view perspective image generation from bird-eye view. BEV, semantics with test-time controllability and generalizability. Unlike prior methods, MVPbev addresses the limitations of neglecting layout consistency, lacking the ability to handle detailed text prompts, and being incapable of generalizing to unseen viewpoints. The first stage of MVPbev projects given BEV semantics to perspective views with camera parameters, enabling the model to generalize to unseen viewpoints. The second stage introduces a multi-view attention module with special initialization and denoising processes to enforce local consistency among overlapping views with respect to cross-view homography. This design allows for object-level control and novel view generation at test time. MVPbev further refines a pre-trained text-to-image diffusion model, enabling test-time instance-level controllability. The method is capable of generating high-resolution photorealistic images from text descriptions with thousands of training samples, surpassing state-of-the-art methods under various evaluation metrics. The authors demonstrate the advances of their method in terms of generalizability and controllability with novel evaluation metrics and comprehensive human analysis. They highlight the significance of their contribution, including a novel multi-view image generation method that produces semantically and visually consistent perspective RGB images from BEV semantics, a more controllable yet extendable algorithm, and state-of-the-art performances on large driving datasets. The authors also discuss related work in image editing and generation, focusing on conditional image generation and novel view image synthesis. They note that while generative models have made significant progress, multi-view or cross-view text-to-image generation still faces issues of computational efficiency and consistency across views. They highlight the limitations of existing work, including MV diffusion, BEV gen, BEV control, and magic drive, which failed to generalize to more dramatic viewpoint changes or smaller overlapping areas, and do not conduct human analysis on image generation quality. MVPbev's method includes a novel training initialization and denoising design to explicitly enforce visual cues at overlapping FOVs to be coherent. The overall pipeline of MVPbev can be found in Fig. 2, with more details of the first and second stages provided in Sec. 3.1 and Sec. 3.2 respectively. The model training process is described in Sec. 3.3. MVPbev is a multi-view perspective image generation model that leverages a latent diffusion model with test-time controllability and generalizability. The model consists of a variational autoencoder with an encoder, decoder, denoising network, and condition encoder, trained using a multi-view LDM loss. During inference, the denoising process generates samples in the latent space, and the decoder produces RGB images with a single forward pass. The model allows for instance-level controllability through a mechanism that manipulates the response of cross-attention layers to accurately guide instance-level synthesis. The model is evaluated on the NuScenes dataset, which provides full 360-degree coverage with 6 cameras, and the evaluation metrics include image quality, visual consistency, semantic consistency, and object-level controllability. The results show that MVPbev outperforms state-of-the-art methods in terms of image quality, visual consistency, and semantic consistency. Human analysis also demonstrates that MVPbev generates more visually and semantically consistent images and achieves better object-level controllability. MVPbev is a two-stage method that projects BEV semantics to perspective views and performs image generation with respect to both text prompts and individual perspective semantics. The authors compare MVPbev with baselines and report its superior performance in Table 1. Visual comparisons in Figure 6 and qualitative results in Figure 7 demonstrate MVPbev's ability to generate visually consistent images from diverse BEV semantics and text prompts. Additionally, MVPbev showcases test-time controllability and generalizability, handling viewpoint changes without retraining the entire model. Experiments are conducted to demonstrate object-level controllability, and qualitative evaluations in Figure 9 and qualitative examples in Figure 10 indicate that MVPbev provides better generalizability and object-level controllability. Human analysis in Table 1 shows that MVPbev outperforms baselines significantly, generating photorealistic yet consistent images and achieving a high rate of correctly generated instances in terms of object color. The paper introduces MVPbev, a novel method for generating multi-view perspective images from bird's eye view (BEV) layouts with test-time controllability and generalizability. This approach leverages a diffusion-based framework to produce diverse and realistic street view images from a given BEV layout. The authors acknowledge the support of the National Natural Science Foundation of China and provide an extensive list of references, showcasing the paper's foundation in various computer vision and machine learning concepts. The proposed MVPbev method consists of a bird's eye view encoder, a diffusion model, and a controllable image generator. The bird's eye view encoder maps the input BEV layout to a latent representation, which is then fed into the diffusion model to generate a diverse set of latent codes. These latent codes are then passed through the controllable image generator to produce the final street view images. The controllable image generator is designed to allow for test-time controllability, enabling the generation of images with specific attributes, such as lighting conditions, weather, or time of day. The authors demonstrate the effectiveness of MVPbev through various experiments, showcasing its ability to generate realistic and diverse street view images from a given BEV layout. The paper also provides a comprehensive review of related work in the field, including image synthesis, diffusion models, and neural radiance fields. The authors highlight the limitations of existing methods and demonstrate how MVPbev addresses these limitations through its novel approach. Overall, the paper presents a significant contribution to the field of computer vision and machine learning, providing a new approach for multi-view perspective image generation with test-time controllability and generalizability.